Welcome to the deep dive. We dig through the details to bring you, well, the clearest picture possible. Today, we've got a story that, honestly, it kind of flips the script on how modern computing got started. Forget the whole Silicon Valley garage myth for a second,
Yeah.
because our sources, they point somewhere else entirely. Older, much more surprising, actually. We're talking military necessity, specifically naval warfare, sparking the whole digital revolution.
It's a fascinating trail to follow, isn't it? We're basically going to walk through how these really fundamental technical solutions grew out of these very urgent, very practical problems, starting with early 20th century naval defense needs and trace it all the way to the complex systems you interact with every single day, often without even thinking about it. And this isn't just like a history lesson. It's about understanding how those deep roots shaped, well, everything digital. We want to reveal those often hidden catalysts, the technical breakthroughs that really made it happen.
And it is quite a story. Understanding this history, it gives you such crucial context for what's happening now in technology. You really see that critical back and forth, between government, universities, and industry. That whole ecosystem is still driving innovation today. It also, frankly, makes you question where big ideas really come from. So, okay, let's unpack this journey you've brought us, starting way, way back. Naval warfare lighting the first digital sparks.
The Naval Crucible forging the first digital computers, pre-digital era to 1950s.
Okay, so to really get this, we need to paint a picture. We're talking early 1900s. The term digital computer, it didn't even exist yet. But naval warfare, it was already incredibly complex, demanding calculations, simulations. What did that actually look like? What problems were they grappling with?
That's exactly the right starting point. So think about the period, say, 1900 to 1925. Naval warfare, especially fire control, aiming the big guns, was a huge area of focus, life or death stuff. Imagine the sheer complexity. You've got moving ships, trying to hit other moving ships, predicting enemy movements, coordinating a whole fleet, plus managing just a flood of real-time information from lookouts, maybe early radio signals. These weren't, neat math problems on paper. They were messy, dynamic, real-world challenges. And they needed fast, precise calculations that the technology back then just dummered with. Well, it struggled to deliver reliably. It was a serious technical bottleneck, and it had huge strategic consequences.
Right, so what were they actually using? I'm picturing gears and wires, something very mechanical, very analog.
You're spot on. These early systems were heavily based on mechanical contraptions, analog electrical circuits, and, critically, a massive amount of manual human effort. Think about a warship's Combat Information Center, the CIC. It's basically the ship's nerve center. You'd have operators feeding in raw data, target bearings, speeds, maybe early radar pings. Then teams of sailors would literally plot this information by hand onto shared maps or plotting tables. It's sort of like those scenes from the Battle of Britain bunker, with people pushing little models around a map but crammed onto a ship rolling in the sea. Commanders relied entirely on this manually updated picture to make decisions, to aim their guns.
Wow. That sounds not just slow, but incredibly stressful and prone to mistakes in the heat of battle. What were the real technical weak points? Where did that analog approach just hit a wall?
Well, there were several big issues. First, just the basic unreliability of analog circuits back then. Lots of moving parts, lots of mechanical wear and tear. Things broke down. A lot. Plus, analog signals are really sensitive to noise, electrical drift, even temperature changes. That meant inaccuracy. Every time data was converted, like from a radar signal to a mark on the map or an angle setting to a trajectory, you lost a bit of precision. Keeping voltages consistent across hundreds of components. Really tough. And then there's the human factor. Plotting everything manually, constantly updating. It introduced delays. And under extreme stress, mistakes happen. Even a tiny error in plotting or calculation could mean missing your target completely. In naval combat, that's catastrophic. So yeah, they definitely hit a technical wall. They had these super complex real-time problems. But their tools were just fundamentally limited in speed, in accuracy, and reliability. And that desperate need for something faster, something more precise, more automatic, that's really where the seed of the digital idea starts to germinate.
Okay, so a massive bottleneck, real-time challenges, analog limitations. What was the breakthrough, the thing that started to change the game? Was it one specific project?
It really was. And that brings us squarely to Project Whirlwind. What's so interesting about its origin is that it didn't start as some grand plan to build a general-purpose computer. Not at all. It came from a very specific, very practical, and during World War II, very urgent request from the U.S. Navy. So in 1944, the Navy goes to MIT's Servo Mechanisms Lab, and they ask them to design a flight simulator. Seems simple enough, right? But their vision was really ambitious. They wanted a simulator that could continually update a simulated instrument panel based on what the pilot was doing with the controls. And critically, it needed a considerably more realistic aerodynamics model than anything that existed before. Its original name tells you a lot, the Airplane Stability and Control Analyzer, or ASCII.
A flight simulator.
Yeah.
Seriously, that's the spark that lit the digital fire. That's unexpected.
How did that relatively narrow goal lead to such fundamental computing breakthroughs? What was it pushing against that forced new solutions? Right. This is where Whirlwind starts to morph beyond just a flight simulator and becomes a real pioneer. By the time it was operational, around 1951, Whirlwind was, and this is key, among the first digital electronic computers that operated in real time for output, and significantly. The first that was not simply an electronic replacement of older mechanical systems. That real-time operation was the absolute game changer. Think about earlier big machines like ENIACs. They mostly worked in batch mode. You fed them a problem, they crunched away for hours, maybe days, and eventually spat out an answer. But Whirlwind needed to respond instantly to the pilot's stick movements, to changing conditions. It needed speed, constant feedback, and it had to be reliable, rock solid. That demand for real-time interaction fundamentally reshaped how they had to think about computer architecture.
Okay, yeah, that's a total paradigm shift. Not just calculating, but interacting constantly, immediately. What other technical firsts came out of Whirlwind?
Another big one was bit parallel calculation. Instead of processing the bits, the zeros and ones, one by one, sequentially, Whirlwind could handle multiple bits at the same time, in parallel. That gave it a huge speed boost for certain operations. But probably the most critical breakthrough, the thing with the longest legacy, was magnetic core memory. This was revolutionary. It replaced the older memory technologies like electrostatic storage tubes, the Williams tubes, and mercury delay lines. Those earlier systems, like an EDVAC or machines using Williams tubes, were notoriously unreliable. Mercury delay lines literally stored data as sound waves bouncing through tubes of mercury. Slow, and they needed constant refreshing to keep the data from just fading away. Williams tubes were better, but still had major reliability headaches and needed constant refresh cycles, too.
Magnetic core memory. Okay, that sounds much more solid. What exactly made it such a leap forward? Why was it so critical?
It was absolutely transformative. J.W. Forrester and Bill Pappian at MIT led this intense effort starting around 1949. They developed these tiny little rings, like tiny donuts made of metallic ceramic material, maybe the size of a pencil lead tip back then. Wires were threaded through these cores, and the direction of the magnetic field in each core represented a 0 or a 1. The key advantages. First, reliability. Data didn't just randomly disappear like it often did with the older tubes. It was stable, non-volatile eventually. Second, speed. They achieved switching speeds roughly 300 times faster than the electrostatic tubes. 300 times. This was the stable, fast internal memory that real-time computing desperately needed. Suddenly, the computer could reliably hold and instantly access much larger amounts of data and instructions, which is fundamental for anything complex. Before magnetic core, keeping Whirlwind running reliably for any length of time was a constant battle. This changed everything.
So stability and speed, the magic combination. Were there other innovations happening at the circuit level or even in how they kept the machine running?
Oh yeah, definitely. They used the Eccles-Jordan flip-flop circuit as a basic building block that's essentially a tiny electronic switch that can hold a single bit, a 0 or 1. Absolutely fundamental for digital logic and memory. And they were constantly iterating. They used vacuum tubes like the 787, which were okay, but they were always looking for better components, even if it meant redesigning parts and changing tube sockets constantly. But what was also really clever, and way ahead of its time, was Whirlwind's built-in self-diagnosis. They actually designed special programs, check problems, and trouble location problems that the computer would run on itself to find faults. And it wasn't just finding broken parts. It could detect marginal components tubes that were about to fail. For instance, they found they could slightly lower the voltage to a specific part of a vacuum tube, and if it was weak, it would fail completely right then. The check problem could then pinpoint the failing tube. It was like early predictive maintenance built right into the machine.
That's amazing for the 1950s. Designing the machine to find its own weak spots before they cause chaos, that must have saved incredible amounts of time. But all this cutting-edge work, constant changes, new memory tech, it sounds astronomically expensive. Was the budget a sore point?
Oh, absolutely. A huge sore point. Whirlwind's costs just kept climbing, which led to some serious pushback. The initial estimate back in 1944 for just the study phase was like $75,000.
Yeah.
By 1945, the estimate for the whole machine, supposed to take 18 months, jumped to $875,000. Later that year, it was burning through $30,000 per month. By 1947, the projection hit nearly $3 million. And get this, by 1949, Whirlwind alone was eating up almost 65%, two-thirds, of the entire Office of Naval Research's math research budget. So yeah, people were definitely asking tough questions, especially as the Navy's interest in the original flight simulator goal was kind of fading.
65%. Wow. How on earth did Forrester and the team justify that kind of spending, particularly if the Navy was getting cold feet about the simulator?
Well, Forrester had this very strong first-class philosophy. He believed in building things right, using the best possible approach, even if it cost more up front. His argument was that it would save time and money in the long run by avoiding endless debugging and redesigns. Quality first. He was deeply convinced, he said, computers offered rewards to the military as great, if not greater than radar. A bold claim back then. But that didn't stop the criticism. There was a major blow-up in late 1948. Dr. Mina Rees, head of the ONR's math branch, basically called them out. She said there was too much talk and not enough machine. She questioned its mathematical competence and compared it unfavorably to John von Neumann's computer project at IAS, which was seen as more theoretically grounded. There was internal debate at MIT, too.
So intense pressure, mounting costs, and the original sponsor losing interest. That sounds like a recipe for cancellation. What saved it? What gave Whirlwind a new lease on life?
Geopolitics, basically. The pivotal moment was the Soviet Union detonating its first atomic bomb in August 1949. That sent shockwaves to the U.S. defense establishment. Suddenly, the threat of Soviet bombers attacking North America felt very real, very urgent. Air defense became the absolute top priority. In response, the Air Force convened the Valley Committee, officially the Air Defense System Engineering Committee, or ADSEC. And this committee took a systems-oriented view. They realized you couldn't just have better radar or faster jets. You needed an integrated system to manage the entire air battle in real time. And they look at Whirlwind, its real-time speed, its potential reliability with core memory, and saw it as the perfect brain for such a continental air defense network. This gave Whirlwind a brand new, incredibly urgent mission, just when the Navy was backing away. The Air Force, through something called Project Claude, essentially stepped in and said, "We need this," effectively taking over the funding and redefining its purpose.
Right, so this project, facing huge technical challenges, budget battles, internal doubts, suddenly gets a new critical mission because of the Cold War. What does that dramatic shift tell us about how innovation happens, especially when military needs and national urgency are the main drivers?
It tells us that innovation is often messy, nonlinear, and driven by necessity. The urgent military requirement, first for the simulator, then critically for air defense, provided the justification and, crucially, the sustained funding for very high-risk, fundamental research. Research that, honestly, private industry probably wouldn't have touched back then. The commercial payoff was just too uncertain, too far off. Forrester's first-class approach, though expensive, forced fundamental breakthroughs like magnetic core memory and real-time processing. These innovations ended up having applications far beyond just defense. That push for realistic simulation, for instance, directly drove progress in real-time computing that influenced almost all business computers later on. It really shows how tackling very practical, urgent problems can spin off fundamental scientific and engineering advances with massive, often completely unforeseen long-term benefits.
And what was the most direct, the most massive legacy of Whirlwind, the system that really scaled up those innovations?
That would absolutely be the SAGE system, the semi-automatic ground environment air defense system built for the U.S. Air Force. The design of Whirlwind was directly adapted, becoming the Whirlwind 2 design, which was the core computer used in every SAGE center.
Okay, here's where it gets really interesting for me. How does a project that started as a flight simulator end up as the nerve center for defending an entire continent? And what were the ripple effects, maybe the unintended consequences of building something on that kind of unprecedented scale?
SAGE was just colossal. Think about the goal. Provide a single, real-time, unified picture of the airspace over North America. Detect incoming bombers, identify them, and direct interceptor aircraft or missiles. It was designed as this integrated real-time control system, a real-time communication system, and a real-time management system. A network of massive, hardened concrete bunkers, each housing enormous computers based on the Whirlwind 2 design, linked to radar stations across the country, processing all that data constantly. The first SAGE Direction Center went live in 1958. By 1963, there were 23 of these centers operational across the U.S. and parts of Canada, each one a technological marvel for its time, with operators interacting via graphical displays and light pens.
That sounds incredibly expensive. If Whirlwind's budget caused controversy, SAGE must have been off the charts.
Completely off the charts. Estimates range from $8 billion to $12 billion in the dollars of that era. That's comparable to the Manhattan Project. It was one of the largest defense projects ever undertaken. But its impact went way beyond just air defense. Here's a critical point. Even though the main threat shifted from bombers to ICBMs after Sputnik in '57, making SAGE somewhat strategically obsolete almost as soon as it was fully deployed, it served as an incredible training ground. This is maybe its most important legacy. SAGE trained literally thousands of programmers, engineers, and technicians in real-time systems, computer networking, interactive graphics, large-scale software development, project management, skills that were brand new. Many pioneers of the modern computing industry got their start working on SAGE in the '50s and early '60s. This massive government project essentially created a huge pool of highly skilled technical talent that then flowed out into the nascent civilian computer industry for decades. It seeded the entire field.
It's the formalization and diversification of computing, 1950s, 1970s.
Yeah, that transition out of SAGE is really key because it marks a shift, doesn't it, for those purely military-driven projects towards computing becoming a formal scientific field and starting to branch out into applications that would eventually reach everyone. And the key ingredients for that were the people trained by SAGE and the development of better tools, especially programming languages.
Right. It wasn't just about building the hardware anymore. It was about creating the language to talk to the hardware and training the minds to use it. So how did computer science actually emerge as its own thing, academically speaking?
Well, the 1960s were really the time when computer science started to formalize as a distinct academic discipline.
Yeah.
You saw major universities, Stanford, Carnegie Mellon around 1965, MIT in 1968, establishing dedicated computer science departments. And often, the faculty in these new departments were people who had direct experience on projects like Whirlwind or SAGE. They brought that practical knowledge. They started building the theoretical foundations, the curriculum, the whole intellectual framework for the field to grow beyond just, an engineering niche or a military tool. This was absolutely crucial for training the next wave of innovators and researchers.
And a huge piece of that puzzle must have been making programming easier, right? Moving beyond the ones and zeros. Grace Hopper's name always comes up here. What was the Navy's role still? And what were her big contributions?
The Navy continued to play a really important role, yeah. They consistently sponsored Grace Hopper and others through the 1950s, specifically to develop what they called automatic programming techniques. And these techniques became the very first compilers. Now, a compiler, just to clarify for listeners, is basically a translator. It takes programming code written in a high-level language, something closer to human language, and translates it into the low-level machine code, the raw instructions that the computer's processor actually understands. This was a massive leap. Suddenly, you didn't need to be a hardware expert writing an obscure assembly language or binary. It made programming accessible to a much, much wider group of people. A huge democratization, really.
She was amazing. I always think of her nanosecond wire demonstration. Such a brilliant way to make an abstract concept concrete.
Yeah, she was fantastic at communicating these ideas. That piece of wire, about a foot long, representing the distance light travels in a billionth of a second, she'd hand it out and really make people grasp the physical limitations of speed in computing and communication. It was brilliant. Beyond that, her technical contributions were immense. She was central to defining common business languages, especially COBOL, the Common Business-Oriented Language. The Pentagon actually pushed for this, convening a meeting in 1959 to create a standard language for business applications, readable and portable. And the first COBOL compilers were ready by 1960, heavily influenced by her earlier work. Even other early influential languages like John McCarthy's LISP, which was crucial for early artificial intelligence work because it handled symbols, not just numbers, also got significant government support. These high-level languages just fundamentally changed software development. They allowed for more complex programs, easier maintenance, and wider adoption across different fields.
Okay, so the government, the military, they're funding hardware, they're funding software tools, and then DARPA comes along, another huge catalyst, right?
Absolutely pivotal. DARPA, the Defense Advanced Research Projects Agency, was created in 1958. It was a direct reaction to the Soviets launching Sputnik, a real wake-up call. The U.S. realized it needed an agency dedicated to high-risk, high-payoff, long-term research to prevent future technological surprises. And within DARPA, one office became particularly influential for computing, IPTO, the Information Processing Techniques Office.
And the head of IPTO, starting in '62, J.C.R. Licklider, he had a really different vision for computers, didn't he? Not just calculators.
A radically different vision. Licklider talked about man-computer symbiosis. That was his key phrase. He didn't just see computers as tools to automate tasks or crunch numbers faster. He envisioned them as partners. as tools for augmenting human thought and creativity. He uses a wonderful analogy of the fig tree and a specific wasp. They absolutely depend on each other for survival and reproduction,
No.
a symbiotic relationship. He saw humans and computers potentially having that kind of relationship where each amplifies the other's strengths, leading to insights neither could achieve alone. It was a profound shift from computation to cognition to partnership.
Augmenting human thought. That's a powerful idea. How did that vision translate into actual funded projects? What came out of it?
Well, Licklider's vision directly fueled IPTO's decision to pour funding into Project MS at MIT starting in 1963. MA was an acronym for several things: manning computer, machine-aided cognition, multi-access computer. Licklider's goal was explicit. He wanted a profound advance in the way of thinking about computing. The big focus was on interactive computing and time-sharing. He really pushed the idea that computers should be for communication as much as they are for calculation. He saw the network coming.
Interactive computing and time sharing. Okay, what were the practical results of Project MS? This feels like it's getting closer to the computers we use every day.
It absolutely was foundational. Project ENIAC was instrumental in, as one report put it, bringing computers out of the laboratory and business and leading it to the home, although that took a while, obviously. Time sharing was key. This technology allowed many users to connect to and interact with a single powerful mainframe computer simultaneously, essentially sharing its processing time. By the mid-70s, time sharing was widespread on mainframes. It made computing vastly cheaper per user. Suddenly, students, researchers, more businesses could get hands-on access. Instead of submitting a job and waiting hours for a printout, you could type a command and get an instant response. Interactivity was born. But MA's influence went even further. It laid the conceptual and technical groundwork for things we completely take for granted now. Early ideas for word processing, text editing, interactive programming environments where you could debug code on the fly, even the core concept behind the electronic spreadsheet. That idea which led to VisiCalc, then Lotus 123, eventually Excel. Its origins trace back to the interactive environment fostered by MS. Plus, the first PC versions of Internet protocols, like FTP software, came out of MIT's Lab for Computer Science, the successor to Project MAC.
So this isn't just about military tech anymore. It's directly shaping the tools for everyday knowledge work, for communication. What does this tell us about how that federal, often defense-related funding ripples out into civilian life in unexpected ways?
It really highlights a crucial dynamic, doesn't it? How does a defense agency end up sparking the creation of your spreadsheet program? It boils down to the nature of funding fundamental long-term research. DARPA, especially IPTO under Licklider and his successors, wasn't just funding specific military gadgets. They were funding broad research areas, supporting centers of excellence like MIT, CMU, Stanford, with large multi-year grants. This gave brilliant researchers the freedom and the stable funding to explore high-risk, foundational ideas like interactive computing, time-sharing, networking. The initial justification might be defense-related better command and control, for instance. But the fundamental breakthroughs often turn out to have incredibly broad applications that nobody predicted at the start. The payoffs are uncertain, but potentially enormous and transformative for everyone.
And speaking of transformative, maybe the biggest legacy from DARPA and IPTO is the internet itself. ARPANET. How did that whole thing get started?
Yeah, the internet's origin story really starts with a core technology: packet switching. This is a radical idea pushed by researchers like Larry Roberts at IPTO and Paul Barron at RAND and Donald Davies in the UK. Instead of creating a dedicated, continuous circuit for a whole conversation like the old telephone network, packet switching breaks the data, emails, files, whatever, into small chunks called packets. Each packet gets an address slapped on it, and they're all sent out independently into the network. Routers figure out the best path for each packet, and they can take different routes. If one path is blocked or busy, they just find another way. This makes the network incredibly efficient. Lines aren't tied up unnecessarily and incredibly resilient. If part of the network goes down, packets can just route around the damage.
Efficiency and resilience. Okay, crucial for military comms, but also just better networking. How did this concept turn into ARPANET?
Well, DARPA decided to build a network based on packet switching to test it out and achieve several goals. They wanted to link researchers at different universities and research centers across the U.S. This would let them share expensive computing resources more efficiently, like accessing a supercomputer remotely. And, yes, building a communication network that could survive damage was definitely a motivating factor, given the Cold War context. So ARPANET started small in 1969, connecting just 4 sites: UCLA, Stanford Research Institute, SRI, UC Santa Barbara, and the University of Utah. It grew quickly, though. By 71, it had 23 nodes, and they did a big public demo in 1972 that really showed the world packet switching worked.
And what about the actual rules of the road, the protocols that let all these different computers talk to each other?
That was the next critical step, the development of TCP/IP Transmission Control Protocol Internet Protocol. This work was led by Vint Cerf and Bob Kahn, with contributions from many others at places like Stanford, BBN, the company that built the ARPANET routers, and University College London. TCP/IP became the fundamental standard, the common language for all communication across interconnected networks, the Internet. It defined how packets should be addressed, sent, checked for errors, and reassembled. It's still the foundation of the Internet today. And almost immediately, useful applications started appearing on ARPANET. Email was the killer app, really. Ray Tomlinson's invention of the user-at-host format made it easy. And FTP, the file transfer protocol, let researchers easily share files and data across the country. This absolutely transformed scientific collaboration. Suddenly, distance wasn't such a barrier.
So it wasn't just connecting machines, it was connecting people and their ideas. How did it grow beyond the initial ARPANET group?
Well, ARPANET proved so useful that demand grew rapidly. First, it expanded within the computer science research community. Then, other government agencies started building their own networks for specific scientific fields, often using ARPANET technology or connecting to it. You had MFENet for magnetic fusion energy research, HUTNet for high-energy physics, a NASA network for space physics. But these were somewhat fragmented. The big unification came from the National Science Foundation, NSF. In the early 80s, NSF created CSNet to connect university computer science departments that weren't on ARPANET. It was hugely successful. That success led to a much bigger vision. NSFNet launched in 1986. NSFNet connected the nation's supercomputing centers with regional networks, creating a high-speed backbone for the entire U.S. academic and research community. It essentially became the core of the early Internet for non-military users.
Okay, so we have this government-funded academic and research network. How did it turn into the commercial internet we use for everything today? That seems like a huge leap.
It was a deliberate, strategic transition managed by the NSF. It's actually a fascinating example of industrial policy. NSF provided the initial seed funding to get NSFNet and the regional networks off the ground. But their plan, explicitly, was always to transition it to the private sector once it reached a critical mass, enough users, enough traffic, enough infrastructure to be self-sustaining. They encouraged commercial use, gradually relaxed restrictions, and fostered the growth of private internet service providers, ISPs. By 1993, the ecosystem was mature enough. NSF decommissioned the NSFNet backbone, and the commercial ISPs took over completely. It's a powerful case study in how sustained federal investment built the foundational infrastructure, nurtured the technology, and then strategically handed it off to become a massive commercial success. And it's just amazing, isn't it? The principles behind the internet you use every single day, decentralized, resilient, packet-switched, came directly out of that early defense and research work focused on efficiency and survivability. A total transformation.
Expanding horizons and commercialization, 1970s present.
So as we move into the 70s and beyond, you see this momentum building. The focus shifts increasingly towards making computers more usable, more powerful for individuals, and commercially viable. And that brings us right to another piece of tech you interact with constantly, the graphical user interface, the GUI.
Right. The mouse, the windows, the icons, the whole point-and-click world. You're saying that also has roots in defense funding. Let's unpack how we got from command lines to clicking on pictures.
We absolutely can. The real visionary work started back in the 1960s, again with federal funding. DARPA and NASA supported Douglas Engelbart at SRI. Engelbart wasn't just trying to make computers faster. He was focused on augmenting human intellect, making them tools to enhance our thinking. His famous 1968 demonstration, the mother of all demos, was just mind-blowing for its time. He showed off his NLS, the online system. It had the first computer mouse, hypertext linking, real-time collaboration, and importantly, Windows on screen. It was a complete break from the old teletype terminals and typing cryptic commands. Engelbart showed a visual, interactive way to work with information.
So it wasn't Apple or Microsoft who invented the mouse and Windows. They just popularized it later.
Exactly. Engelbart laid the conceptual foundation. Then, researchers at Xerox's Palo Alto Research Center, PARS, picked up these ideas in the early 70s. They developed the Xerox Alto in 1973. It was basically the first modern personal computer prototype. It had a high-resolution bitmap display showing graphics, a GUI with overlapping windows and icons, a mouse, and it was networked using Ethernet, which PARC also invented. But Xerox, while they didn't really capitalize on it commercially, it mostly stayed in research labs. It took almost another 2 decades for those ideas to hit the mainstream, primarily with the Apple Macintosh in 1984, and then Microsoft Windows really taking off in the early 90s. It's that classic pattern again. Foundational research, often government-funded, pioneers the concepts. Then industry, sometimes much later, figures out how to package it, refine it, and sell it to the masses.
That's a really long delay for something so fundamental, almost 20 years. What about making the computers themselves faster? What advancements were happening inside the box?
That's where reduced instruction set computing, or RISC, comes into the picture. The basic idea behind RISC were to simplify the set of instructions. The computer's main processor, the CPU, has to understand and execute. Counterintuitively, the theory was that a smaller, simpler set of instructions could actually be executed much, much faster by the hardware. Fewer, faster instructions beat more complex, slower ones. IBM did some really pioneering work on this with their 801 computer project back in the 70s, but IBM hesitated. They were worried that these faster, cheaper RISC machines might steal sales from their incredibly profitable mainframe business, the classic innovator's dilemma.
So they didn't want to disrupt their own cash cow. Did federal funding step in again to push RISC forward?
It did, yes. DARPA played a crucial role here, too, as part of its big push on very large-scale integration, or VLSI, basically, how to design and build more complex microchips. DARPA funded parallel university research projects. At UC Berkeley, David Patterson led the development of the RISC-4 and RISC-2 architectures. At the same time, over at Stanford, John Hennessy developed the MIPS architecture. Both were funded by DARPA. Their work proved the concept. Simpler instruction sets did lead to faster, more efficient processors. They focused on optimizing how computation, storage, and communication work together on the chip.
And this time, industry jumped on it much quicker. It didn't take 20 years.
Much quicker this time, yeah. There was rapid adoption by industry. Sun Microsystems based their Spark architecture directly on Berkeley's RISC-2. MIPS Computer Systems commercialized Hennessy's work. Hewlett-Packard got heavily into RISC. Even IBM eventually embraced it with their PowerPC architecture, developed with Apple and Motorola. By the mid-90s, RISC processors dominated the high-performance workstation market, a $15 billion industry back then. They largely displaced the older, more complex instruction set computers, or CISC designs in that space, and technically RISC was a huge enabler for things like interactive graphics and virtual reality. Companies like Silicon Graphics, SGI, were major early adopters. SGI used RISC chips and innovations like the geometry engine, which SGI's founder Jim Clark had worked on with DARPA support, to build incredibly powerful graphics workstations used for everything from scientific visualization to Hollywood special effects.
That makes sense. Graphics need raw processing power. Okay, let's shift gears slightly to something that still feels cutting edge, but also has these incredibly deep roots. Artificial intelligence, AI.
AI is another perfect illustration of how crucial that long-term federal investment was. In the early days, pretty much all the funding for fundamental AI research came from federal sources, especially DARPA. They were funding the exploration of ideas like Licklider's man-computer symbiosis, supporting pioneers like John McCarthy at Stanford, who created LISP, the main AI programming language, and Marvin Minsky at MIT. Big companies like IBM and AT&T, they had small AI efforts in the 50s, but often pulled back because the commercial payoff seemed so distant and uncertain. It was just too speculative, too blue sky for their bottom lines back then.
So the government essentially provided the patient capital, the long-term vision, to allow AI to even develop as a field in the first place.
Precisely. Let's take speech recognition as an example. It really shows the long time periods between initial research and development of successful products. Early work started way back, with statisticians, electrical engineers trying to figure out basic phonetics and signal processing. Then DARPA contracts became critical. They funded companies like Dragon Systems through the 80s, pushing specifically for large vocabulary, speaker-independent, continuous speech recognition. That's the holy grail, right? Understanding anyone speaking naturally, not just trained words. It required major breakthroughs in statistical modeling, computational linguistics, really hard AI problems.
And when did all that patient investment finally lead to products you could actually buy and use?
Well, it took decades. Dragon Systems had the first commercial PC speech recognition product in 1984. It let you speak commands, open files, but it was slow, often needed discrete words spoken clearly. It wasn't until the 1990s, fueled by more DARPA funding and faster processors, that Dragon and others like Lucent started offering robust, continuous speech systems that were actually practical for things like dictation. That paved the way for the voice assistants you use today. Another big area in early AI was expert systems. These were programs designed to capture the knowledge and reasoning process of human experts in very specific, narrow domains. Like Dendril, developed at Stanford with federal money, which could analyze chemical data to identify molecules. In the late 70s, early 80s, expert systems were hyped as the first real commercial products of AI research. They had limitations that were often brittle, meaning they failed badly outside their narrow expertise, but they showed the potential and evolved into more sophisticated knowledge-based systems.
And the underlying computer science theory kept advancing alongside these applications.
Absolutely. Foundational concepts, like the theory of state machines, basically, a mathematical model of computation where a system transitions between states based on inputs, like a vending machine reacting to coins and button presses. That concept became incredibly important and refined during this period, supported by federal funding. It's fundamental to how compilers work, how operating systems manage tasks, how network protocols function. It's everywhere in computing. You can even see the commercialization trend in patent data. Between 1985 and 1996, there was an explosion, exponential growth in patents related to AI. This showed AI wasn't just research anymore, it was being embedded as components within larger commercial systems in industrial controls, in cars and software. The transition to real-world application was happening.
So again, that long winding path from theory to embedded tech. What about virtual reality and computer graphics? It feels very visual, very modern, but you're saying it also goes way back.
Way back. Its earliest roots, arguably, go right back to Project Whirlwind in the late 1940s. That was one of the first computers to have a visual display, a cathode ray tube showing graphical output in real time. And its successor, Sage, heavily used interactive graphics consoles. Operators used light guns, early pointing devices to select targets directly on the radar screen.
So the idea of seeing data visually on a screen and interacting with it directly started with air defense.
Pretty much, yeah. Then you get seminal figures like Ivan Sutherland in the 1960s. He had this vision of the ultimate display, a system that would let you see, hear, even feel a virtual world, total immersion. His PhD work, the Sketchpad system from 1963, let users draw directly on screen with a light pen. It was revolutionary. And then in 1968, he demonstrated the first real head-mounted display, essentially the ancestor of today's VR and AR headsets, and his groundbreaking work, funded by a whole mix, the CIA, RRPA, later DARPA, the Office of Naval Research, Bell Labs, the Air Force, a real cross-section of government and industry recognizing its potential.
That's a wild mix of funders for something that now feels so tied to gaming and entertainment.
Sutherland's influence was massive. He helped establish major academic centers for computer graphics, MIT, Harvard, and especially the University of Utah, which became a hotbed of graphics research in the late 60s and 70s, producing many industry pioneers. And the applications quickly went beyond just drawing or military sims. VR research found niches in science and medicine. Project Whirlwind, started at UNC Chapel Hill in 1967, is a great example. They develop haptic interfaces devices that give you force feedback. Researchers could literally feel the forces between molecules as they tried to dock them together, helping design new drugs. That was funded by NIH, DARPA, and NSF together.
Feeling molecules, that's incredible, a really tangible benefit.
Yeah.
How did it eventually cross over into the big commercial markets like entertainment?
It was really driven by advances in the underlying hardware faster processors, specialized graphics chips. Companies like SGI, which we mentioned earlier with RESC, were key. They built powerful machines optimized for graphics, fueled by those faster chips and innovations like the geometry engine developed under DARPA sponsorship. This made high-end graphics and visualization more affordable and accessible. And then the entertainment industry, especially video games, became a huge driver. The demand for more realistic graphics, faster frame rates, more immersive experiences pushed graphics hardware R&D relentlessly. So you get this interesting synergy. The military continues to fund R&D in immersive training environments, network simulations like the HLA standard, realistic computer-generated characters, while the commercial entertainment world pushes the boundaries of rendering, interactivity, and affordability, often using technologies with military roots. It's a cycle where both sides benefit and push the technology forward.
Overarching themes and enduring legacy.
Okay, so we've traced this incredible path from naval gunnery calculations all the way to virtual worlds. When you step back and look at this whole history, what does it really tell us about the role federal funding played? It seems like it was absolutely fundamental, the bedrock.
It was undeniably foundational, and there's a solid economic reason for it. Economists talk about market failure in the context of basic research. Long-range, fundamental research. the kind where commercial applications are distant or uncertain, or where the knowledge created benefits everyone, it's a public good. Well, private companies often can't justify investing enough in it on their own. The risks are too high, the payoff too far off, and they can't easily capture all the benefits exclusively. So government steps in to fund that foundational layer because the benefits to society as a whole are potentially massive, even if no single company can monetize it easily at first.
So it's more than just grants. It's like investing in the shared infrastructure, the fundamental building blocks for future industries.
Exactly that. Agencies like the DoD, NSF, DARPA, NASA, DOE, they consistently provided substantial long-term funding for computer science and electrical engineering research. Often, their investment in the early, critical stages equaled or even exceeded what industry was spending on basic research. And it wasn't just money for projects. Federal support was crucial for building human capital funding university research, supporting graduate students with fellowships. This dramatically expanded the number of PhDs, creating the expert workforce needed. Plus, they invested in shared infrastructure university computer labs, national supercomputing centers, places where academic and industry researchers could come together, collaborate, and share ideas rapidly.
It really sounds like a complex ecosystem, doesn't it? Not just a simple pipeline from lab bench to store shelf.
You've nailed it. It's all about the nonlinear nature of innovation. This history completely blows up that simplistic linear model. Basic research leads to applied research, leads to product development, leads to sales. It just doesn't work that way. What you see instead is this dynamic, messy interplay. New companies spin out of universities, sometimes based on federally funded research. Old companies might stumble, but their people and ideas move on. University research directly spawns products and businesses, often in roundabout ways.
Yeah, not a straight line at all. More like a tangled web or a winding river with lots of unexpected turns. What does that messiness tell us about how we should approach big technological challenges today? Where should the focus be?
It tells us that flexibility, patience, and investing in foundational capabilities are key. Look at the examples. Relational databases. IBM had the initial idea, but it was NSF-funded work at Berkeley that really developed and commercialized it. RASC processors. IBM did early work, but DARPA funding at Berkeley and Stanford pushed it into the mainstream. The internet itself. DARPA's ARPANET, then NSF's NSFNet, then commercial ISPs. The initial goals often change completely. ARPANET was about resource sharing. Its biggest impacts were email and the web, totally unforeseen at the start. This history strongly suggests that investing in fundamental science and engineering, even without a specific product in mind, is incredibly valuable. It creates options, it builds capabilities, and it often leads to transformative breakthroughs in completely unexpected directions. You need to explore broadly.
And what about the people moving between these sectors? Academia, government labs, private companies. How important was that flow of talent and ideas?
Absolutely critical. That fluidity of personnel is maybe one of the most effective yet often underestimated mechanisms for technology transfer. Researchers take their knowledge, their experience, their networks with them when they move. Remember the Bakers moving from IBM Research to Verbex, then founding Dragon Systems. They literally carried the speech recognition expertise across organizational boundaries. And collaborations matter hugely. Partnerships between universities and industry build communities. They speed up information sharing, leading to faster adoption. IBM got into core memory so quickly because their engineers were working alongside the MIT team on Sage. That close contact accelerated everything. And you also have to credit the flexible management style within some of these funding agencies. Program managers at places like DARPA and NSF historically had the ability and the mandate to adapt programs based on early results. They could recognize unexpected value, even if the original milestones weren't perfectly met. Finding that balance, holding researchers accountable, but also allowing for the inherent uncertainty and serendipity of discovery that was really crucial for letting many of these innovations flourish.
Right. So connecting all these threads, it seems clear that these military projects, these academic grants, they weren't just about solving specific technical problems. They were inadvertently, maybe sometimes deliberately, building the foundations of an entirely new global economy, the digital economy that, you listening are completely immersed in today.
That's the big picture, absolutely. This whole innovation ecosystem, heavily fertilized by decades of federal investment, directly enabled U.S. companies like IBM, Intel, Microsoft, and many others to become dominant players in the global computing market. It sparked entire new service industries. Just look at computer and data processing services, generating hundreds of billions in revenue. And it created millions upon millions of high-value jobs in information technology that simply didn't exist before. This history is a powerful reminder that sustained, strategic investment in fundamental research and technology, even when initially driven by government or defense priorities, can have profound, long-lasting, and transformative economic consequences for everyone.
What a fascinating deep dive that was. We've journeyed from the desperate need to aim naval guns more accurately, all the way to the ubiquitous digital landscape that surrounds us now. From Project Whirlwind's real-time computing breakthroughs driven by flight simulation, to the massive Sage Air defense network that, almost as a side effect, trained a generation of computer pioneers.
Exactly. And we saw how that led to the formalization of computer science, the crucial development of compilers in languages like COBOL and LSP, often with continued military and government backing. Then DARPA's visionary push for man-computer symbiosis through Project Mac, giving us time-sharing, interactive computing, and of course the ARPANET, built on packet switching and TCP/IP, which became the very foundation of the internet.
Right, and then following that thread through to the graphical interfaces, the mouse you use every day, the speed boost from RIC processors, the long patient development of AI leading to things like speech recognition, and even the immersive potential of VR and computer graphics. Each step profoundly shaped by that complex dance between government funding, university research, and eventual industry adoption.
Yeah, the impact of those early choices, those foundational investments, just immense. And often, as we've seen, completely unexpected. It really wasn't a straight line. It was messy, non-linear, full of pivots and surprises. But that federal support for the high-risk fundamental work the stuff industry might not have done alone, that seems to be the consistent thread, the enabling factor time and time again.
So, thinking about today, if past breakthroughs were often sparked by shifting strategic needs, Cold War defense, scientific collaboration, economic competitiveness, what unforeseen challenges or maybe opportunities might be driving the next wave of foundational digital tech right now? Maybe in ways we can't quite see yet. Think about it. How might today's highly specialized research, maybe in quantum computing, maybe biointerfaces, maybe advanced materials, how might that become tomorrow's everyday, ubiquitous technology, changing your world in ways we can barely even guess? Something to ponder.